Welcome to the Efficient Energies webinar series. Today we are having our third part of the series, Instrument Transformer and Relay Selection. Q&A is open and we will run live polls during the session. So if you have any questions, you can drop in Q&A session. Uh, Today with us we have two industry experts as a panelist who will guide us through the session. Mr. Rajan Mehta, who is CEO of Efficient Energy Consulting Private Limited, and Mr. Prasad Gore. Mr. Rajan Mehta, he comes with 24 years of experience in power quality, reliability, electrical optimization. He is a chartered electrical engineer, also part of National Standard Building Committees. He has written IS 17036 of power quality. He has worked with 2 megawatt to 150 megawatt of data center projects across India and US throughout the project life cycle. He has led 200 advanced power system studies, voltage stability, harmonics, power quality, power system studies across India, and also executed the testing and commissioning practice for more than 300 megawatt of greenfield data centers. He is an expert in L1 to L5 complete MEP testing in data centers. So he's a leading efficient energy data-driven electrical testing and commissioning practice, bringing deep expertise in PDC, load flow, arc flash, reliability analytics, and for especially for mission critical infrastructure. So I will request Rajan sir to take it forward.
Thank you, Nikhil, as always, and really pleased to be continuing on this series from our side. And I thank Prasad, my colleague and co-host, for this webinar. Prasad, again, to reiterate, brings also more than 20 years of experience in the electrical domain, especially with more than 10 years with a deep dive into the production schematics, your power system studies, and various other advanced network studies. I call him our Chief Power System Week Officer in Efficiently because he's always trying to find out something which is not available online. And that's what has been kind of our motivation to continue this series to bring out concepts and theory, practical knowledge about areas and issues which are not easily, experienced by or not easily known by protection engineers, known by facility engineers in their facilities, and they grapple for answers for these difficult situations when there is a tripping happening and there is no answer for that, or there is no clear logic which provides an answer to the tripping. So, quick recap, this is a third webinar in the series, and we have had two other webinars earlier, which is the first one focused on tripping characteristics of devices. Low voltage devices primarily we focused on. And we also spoke about CTI, a very important concept, your coordination time intervals, which allowed us to set the base for protection coordination, right, in different kinds of network topologies. Then we went into the next series was for short circuit and device duty calculations, which again was a very critical input for understanding and evaluating and conducting proper protective device coordination. And that then leads us to this third webinar in this series, which to my mind is a very important aspect, with respect to protection system. And it kind of feels to me as, you can think of the whole protection relays and the switch gears and everything as a nervous system of a human body. Your skin, your senses, these are all acting like instrument transformers in a way, sensors, CTs, PTs, etc. They're constantly monitoring what is happening around you. When you touch something hot, those sensors instantly send a signal to your brain, which in my opinion is a protective relay, and that decides whether it's a small discomfort, it's something that you can handle, or it's an emergency requiring immediate action. And so your muscles pull your hand back, which means your breaker operates to prevent the damage. So the relay is your brain, the breaker is kind of the muscle, and without the CTs and the relays, right, which is the core of today's webinar that we are trying to deep dive into, the power system would be like, a body without reflexes, very slow, unsafe, and vulnerable. So what the importance of these devices and these sensors cannot be overstated. They play a very big role in ensuring that systems are safer, systems are reliable, and they will behave in the fashion that they're expected to. Now, that's what brings us to the fact, some cases, a lot of places we find where relays do not trip, even though the settings have been properly installed. Right? We get a lot of questions from clients. They pick up the phone and will call me, one of our engineers. Was you have given तुमने device coordination relay settings वगैरह दिया है, हमने सब कुछ implement कर दिया है बराबर से, but still relay strip नहीं हो रहे, relay मतलब fault हो गया and still the relay, no relay operated. So that is in in some ways it is called as a ghost tripping, where it either it did not trip at all, or it tripped and you do not know the reason why it tripped. So one of the key areas here, which is kind of today's topic that we are going to be taking on, is about instrument transformers and relay selections. And the first in instrument transformers, which is most important for all of us to really deep into, because they play a big role, is current transformers. These current transformers will play a very outsized role when it comes to ensuring that relays are behaving the way they are supposed to. Relays are tripping the at the time and the magnitude at which they are supposed to trip. So what does happen when that CT doesn't operate in the zone that it is supposed to operate? What does happen when a CT gets saturated? That's one of the key areas which is ignored when it comes to functioning of these relays. And second part of the webinar, so that will be the first part which we'll be focusing on. In instrument transformers, we are not going to be covering other transformers. We realized that covering just CT, doing justice to CT saturation and its impacts on protective relay, coordination or protective device coordination in itself is a very critical subject, and which will require a certain amount of deep dive. And the second part of the session, we will talk about a brief around expanding on the various relays, protective relays, based on certain equipments, say for power transformers, for the HV networks, for generators, for motors, maybe for busbar protection. What are the typical applications? What are the requirements? Again, not trying to go too much in detail there, because that information you can kind of find online. But the first part of the session, I am very excited for you to deep dive into. And obviously, I'm also going to be learning quite a lot from my team member. So with that, I will hand over to Prasad to take this forward, and hope you enjoy the session. And please feel free to drop Q&A. The more you interact, the more it will help us to curate the session to your needs.
Yeah, thank you. I'm just sharing my screen. Okay, can you just check the screen is?
Yes.
Yeah. Okay, now we will always, as always, we will be starting the session with the question first.
Yeah. How many of you do you really? I mean, this is just a necessity for us to understand. Whether or not it is a standard practice being followed by you in your with by your, not necessarily by you. It might be due to your design consultants who are considering it during the design phase. It can be due by your whoever is doing your relay coordinations. Are they considering that, or whoever is implementing your settings, or whoever is troubleshooting, if at all there are any problems happening. So would love to get your feedback as to, do you think whether these considerations of city saturation, etc., and its preventive measures are being considered in your projects or in the projects to come? Would love to have your feedback. Okay, so yes, we find almost that's not what I'd expected. Almost 85% are saying that they do consider city saturation. That will be very interesting to know that city saturation is a consideration while doing relay protection, relay coordination. All right, so we can go further, I think, Nikhil.
So the next, again, okay, you are considering, so we just want to understand, do you have any idea what is 5P20 cities? So what is the 20 signifies here?
Back to basics.
Okay, what the answer?
Answers, let's see. Yeah, there is a mixed bag. I think we still have around city burden is the most voted. I'm spilling the beans here, but it may not necessarily be the right answer. Okay, so I think the answer is not what the majority is, I think.
There's actually, this is accuracy limit factor.
Yes.
So the first is your percentage accuracy. P stands for it is a protection current transformer, and the 20 stands for accuracy limit factor 20. So that means up to the 20 times of the primary current or the secondary current, the accuracy limit will be plus minus 5%. So this is basically the meaning of this 5P20 CT. So in protection, we normally get 5P20, 5P10. Okay, so as Sir said, the saturation is mostly at the design stage, it should be taken care of only. After that, the saturation that we can think upon when there is no proper tripping root cause, we are not able to get the proper root cause. So first of all, we'll go into the basics of what is saturation means. So now everyone knows the saturation means the core is gets saturated. The core gets saturated means the flux inside the core, that is the flux density of that particular core material or the core size, is completely fulfilled, that is saturated. So here, basically, in terms of current transformer, what we are saying when there is a saturation means, here you can see this is your secondary current and this is your primary current. So when cities get saturated, that means your IS is not equal to IP. So whatever secondary current that is seen by the relay will not be exactly equal to the what is actually fault current or what is actually the abnormality seen in the primary. So this is the main reason wherein we have to take care of the saturation, because the fault current, actual fault current will be different, and the current sensing at the relay will be different if this sensor, that is current transformer, is not working in its unsaturated zone. So basically what happens, we'll go with the very physics or a microscopic level to understand what exactly saturation means, what exactly the magnetic flux lines that means, and what exactly the flux density that means. So herein I will go through, I'll just run through the city first, and then you can correlate the transformer overfluxing, then you can correlate the overfluxing of the motors. Once you understand the physics of the magnetism or the saturation inside the iron cores. Okay, so my intention here is to go to the basic here, to the level wherein the saturation part for you will be understood for your rest of the career or rest of the life, you can say. So what we understand in what we know is that the induced EMF. So VS is here is the induced EMF. That secondary side will be VS, that is induced EMF. That induced EMF is because of the primary current magnetic flux. So we know with the laws of electromagnetic induction, VS, that is induced EMF, will be always equal to rate of change of flux that is happening inside the core. So what happens is here in the primary current, which is the source of a magnetic field strength, uh, pushes all the magnetism inside the core. And how is at a microscopic level how it's happening is, we know that this is your current graph, and we know we what we have learned is this is because the voltage is generated because this is a sinusoidal wave. This is a changing current, and it produces a changing magnetic flux. That's what we have learned so far, and this creates a voltage in the secondary, because this changing magnetic flux is associated with the secondary coil, and the voltage is induced in it. Okay. Even in the primary, the back EMF is induced because of this changing flux. So what does this changing flux exactly mean? So whenever there is a external force, magnetic field force, that is acting upon this core material, what it does is actually, if you see at each level, your flux values are different. So this is your flux and this is your current. Both will be in phase. Okay, and this is your phi m. Phi m is maximum flux lines that can come across this core. So what happens here, if you see everywhere, the flux changes, and this in turn induces the EMF like this. The EMF will not be in the phase, obviously, but just to understand where the induction of the voltage come from. So when you know that there is a flux change, so what will happen every time? These are basically the magnetic dipoles. So these magnetic dipoles, when they align in the when they orient or align in the direction to the flux lines, and then we say this is the magnetic flux lines inside the magnetic core or inside the iron core. So what happens? So every point, if you see, there are many magnetic dipoles exist in the core, and what happens at every instance, these number of dipoles alignment gets increased. So initially, it is only this number of magnetic dipoles are required to align. At this, it will be increasing. So all this dipole orientation is always increasing, and that in turn satisfy the Faraday's law, and in the output of this secondary you will see the voltage gets generated. But in saturation, what happens? All these dipoles are now aligned, and there is no further room for the dipoles or for the magnetic field to have more dipoles to be aligned. So now what happens here? There is a saturation. Means now the magnetic flux lines are completed. Now this core cannot accommodate further increase, or there is no magnetic dipole exists for the orientation. So basically, if you see the magnetic flux at the saturation phi1 and after some time interval phi2 will be same. So the difference will be 0, and here the Vs now will be 0 upon dt. So that is 0. So at this moment, at the saturation point, the voltage drops completely to the 0, and as the voltage drops to the 0, the secondary current will also drop to 0. So this is where the saturation brings a trouble for a relay to understand the exact primary current. So what happens? I think here, just to understand further, we have some burdens connected. Burdens means relay connected. So initially there is no current, so there is no flux lines. As the primary current goes on increasing, there is a flux lines that is associated with the secondary winding, and then based on the burden level, the voltage induced and the current passes through the relay. So this occurs till the saturation point. So till the saturation point, Is is exactly the replica of the primary current. So in this case, now further, I think now you must have seen, because earlier now what I was very few years back only I came to know about this magnetic dipole alignment, and which is causing the saturation, because saturation topic is very difficult to understand at the initial level with respect to this much of understanding. If you go into the physics of the magnetic dipole, then it becomes a very good understanding where exactly the flux is changing and how the voltage is getting induced. So initially when I read the paper somewhere few years back, somebody said the secondary voltage drops to 0. So I was like, if current is going, everything is there, magnetic flux lines are there in the core inside, but how then the voltage goes to 0 all of a sudden at the saturation point? So when I gone through the complete book of magnetism, then I understood the magnetic dipoles, its moments and its orientation. Okay, so I think this is the only one thing I just wanted to have included in the basics. Further, we have actually two kinds of saturation. One is symmetrical saturation and one is asymmetrical saturation. Basically, what happens in a symmetrical saturation is you have the fault current, which is very symmetrical, and there is no DC component. So initially what happens, your secondary current is following the exact primary waveform, and here the saturation occurs and this current will start to drop to 0 because the voltage drops to 0. Then in the negative half, again the magnetic dipole orientation reverses, and then again it will have it will follow the path, and again at saturation this will go back. So this is your actual primary current, and then this will be your secondary current sensed by the CT, saturated CT. So this is symmetrical. So symmetrical at the very first cycle, if there is a saturation, you will come to know. In asymmetrical saturation, what happens? Asymmetrical means the waveform is not symmetrical across the origin line. So this is your origin, and it is not symmetrical across. So here what happens in a positive cycle, the magnetic dipoles start oriented, but here the level is not up to the saturation level. Here what happens in the negative half, you can see negative half is very small. So very small number of dipoles gets aligned to the reverse direction. And here again, it starts to align in the positive. But here, if you see, most of the dipoles have already aligned in the positive. Very few goes to the reverse direction. When again this cycle comes, so there are very few dipoles left with the reverse direction. And because of this, here you will get a very heavy saturation. So here, this will be the secondary current. So in unsymmetrical, asymmetrical fault, you will see at initial cycles, you may see the relay is showing the correct replica of the primary, but after few cycles, it vanishes and it gets saturated because of the because there are no dipoles left for a reverse. So this is also brings to another topic, that is remanence. So remanence, you must have seen, if there is a remanence inside the core, then again it is as good as this thing. So the dipoles are already aligned and you have very few dipoles left to align. So if there is a remanence, this will act as a saturation. So the mitigation part, I will talk about remanence in more detail, not more detail, but we'll see what is remanence means. Okay, for a IEEE, we have one saturation calculator which is free and which is developed by the IEEE itself. Okay, so I'll just show you that. Okay, so this is the Excel prepared by the IEEE members. Okay, so here if you see the blue color part is your actual primary current and the black color part is your saturated CT output. So and the blue color here, this is RMS value and this is the instantaneous value. So black color, again you can see the actual RMS is at a higher side, but the CT is giving the lower output than the actual fault. This is all because of the CT saturation. Now, if I want to improve this, what I can do is, here you can see, here you can see the voltage. The new voltage is 400 volts. If I make it, let's say 800, you can easily see now because of the asymmetry, as I mentioned before, here you will be seeing that at the starting, the secondary current is a replica of the primary. But as the current goes further into the asymmetrical mode, uh, then there is a difference again. And after a few cycles, when the saturation ceases off, then it will follow the secondary. So what we can do here is also, if we can see, if I change the X by R of the circuit, then also
You can use the mouse.
yeah, X by R also it will affect the calculation. Now you can see the error which was very high. Now it was reduced. So the burden and everything, if it is calculated before the design of the cities at the design level, then also you can have the exact uh, proper city selection done before it is installed. So the short circuit study till now we were using for the device duty, mainly for the device duty, but this is one of the use wherein you understand the worst case fault, you understand the X by R, you understand the asymmetry which is going to be there in your distribution, and accordingly you can design your CTs.
It's a very important area which designers, especially design consultants, can take into account. We are really not sure, nor have we seen this level of detailing being done by a lot of consultants, but it's something for some of the projects where we have mission criticality, it can be something that can be definitely taken as an input much early on, working on the short circuit calculations much early during the design phase, and as a result, giving manufacturers the way in which the CTs to be designed, manufactured, and so on. I think now we get into some real case studies, a lot of theory, which Prasad has deep dive into. Let's get into some practical cases of why moil operation happens due to saturation.
The first is we mainly hear this very lot that ground fault operate during charging of the transformer, and the solution for this is we know that we have a second harmonic blocking, and then we do it in a, basically most of the people, they do it in a phase fault, and they activate phase fault second harmonics blocking. But in the ground fault, how is the current should get reflected in a ground fault? Because in the transformer primary, we normally use a residual type of scheme for a ground fault detection. Okay, this is one case that we normally hear a lot. Then there is a second case we always see very often. That is when there is a line-to-line fault on a load side, but the upstream relay operates on residual ground fault. Actual case, there is no ground fault happening on the load side. There is a simple line-to-line fault. Yeah. But the upstream relay trips, and everything looks normal. But when we kind of do the RCA, the first doubt that comes in our mind is the city saturation. So how does this happen? We have got one waveforms which will explain. Okay, I will just zoom in a bit. Okay, so here you can see this is basically, okay, so when I do a pen, okay, so this is you can see there is a line-to-line fault.
Can you use a laser pointer?
So here you can see there's a line-to-line fault, exactly equal and opposite waveforms that you can see in two lines. Okay, but here in the ground, residual ground, this much amount of current is seen. This is RMS value, it's not a waveform, but this is seen. This is basically what happens when in this location, one of the CT gets saturated. So because of that, it for this higher fault, one of the CT and the upstream gets saturated, and it sees it as a ground fault because it is calculated on a residual basis. So the residual basis calculation means is this is your IN is your IA plus IB plus IC. Now everything is perfect, then IN will be 0. But suppose one of the CT is not showing the exact current, or it gets saturated. So then this will bring in a unbalance, and then IN will be more greater than a 0. And if it is in the range of pickup, because for a ground fault, generally the pickup is in percentage of 10 to 20% range. It is very low. So it is possible that this IN can go more than 20% or 10%, and the relay picks up on a ground fault. The same case happens with the charging of the transformer. If you know the charging of the transformer, sometimes the current goes more than 16 into rated current, 16 into IN. So in that case, in first few cycles, what happens is one of the CT gets saturated, then this equation comes into picture, and because of that, IN is greater than 0, and it picks up on the ground fault, even though there is no ground fault. So these two cases, I think you must have realized in your projects also, this is happening, that some ground fault is not there, still the relay is operating on a ground fault. The fault is somewhere else, and the relay on the ground fault is operating at somewhere else. So these kind of things can be because of the saturation of the cities. So in some of the projects now, we normally now see in many projects, the transformers are, let's say, of 2000 kVA or a 2500 kVA. The cities at the primary are normally in the range of 100 ampere to 200 ampere by 1 or by 5. Okay. So because now the network is getting bigger, at the 11 kV side or at the 33 kV side, the fault is maybe in the range of 20 to 30 kilo ampere sometimes. So 20-30 kilo ampere, if you can see, and if you are using this 5P 10 city or 10 cities. So 10, as I said, this is a ALF, that is accuracy limit factor. So up to 10 times of the primary, that is 10 times of the 100, you can see only 1000 ampere. So at up to 1000 ampere, it can guarantee you a 5% error margin. But fault of 20 kilo ampere, that is almost 200 times 100
to 20 times,
not 20 times,
20,000.
200 times. If it goes, then it is expected that these cities will heavily saturate, and this will not operate as intended. So even if your relay settings and everything is perfect, and your cities are not well coordinated, then there is a chance that your primary transformer relay will not pick up, but your upstream breaker or upstream MV level may be tripped. Because if you see your 100 or 200 ampere city at the transformer level, so upstream it might be not more than 500 ampere by 5, or let's say 300 ampere for two transformers. It may be maximum of 300 ampere by 1. So there is a possibility that 300 ampere one may also trip. Okay, the third point is underestimation of the pickup value. So if you see the same case where you have 100 ampere CT and you are setting it at 80 ampere. Here is the case. Here 80 ampere is set. Okay, and the fault is actually a 20 kilo ampere. So it's a heavy fault, and so this CT will not handle this much fault. So it is kind of showing this kind of waveforms on the your DRs, disturbance recorders. Okay, so if you see the saturation level and the measurement after the cosine filter, because every relay is having the cosine filters uh, just to filter out the unwanted harmonics. So this pink line is actually read by the relay. So this pink line is very well below the pickup. So even if there is a fault on the secondary, but just because your city is heavily saturated, this relay will not at all pick up, because it will not reach to the pickup value at all. So there are some advanced relays are there, wherein instead of cosine filter, you can use peak filters. So this green line is basically the peak filter value, which is taken from the peak filter output. Again, if you see, the peak filter is also very close to the pickup. So it is not guaranteed even the peak filter will be working in this scenario. So this is the third case where the city saturation means, because the fault, a fault occurs, but there is no tripping of the relay. Okay, then there is issues with the distance protection. So distance protections, if you know the very basics of the distance protection, it is for the line protection. So at generation, you have the line, right? And normally we may sometime we set it at 80% of the impedance for this, or maybe we set it for 70 to 80% we set it. Then what happens is, if this CT, which is installed for a distance protection, if this CT gets saturated, this will not will be obeyed. So what will happen, if there is a saturation in this city, instead of 80% of the line protection or 80% of the fault coverage, it may see a fault at a reduced level, that is maybe possibly 50%. So at what time the city gets saturated, that tells you what maloperation it will have. So if there is no saturation, all 80%, it is all covered. But if suppose uh, maybe a 7 millisecond, if it is getting saturated, then it will be in the range of 15 to 20%. So even in the distance protection, the saturation becomes a very big problem. Then there is issues with differential protections. Now differential protection, you know that this is what is differential protection. We are covering this, right? So this is your equipment unit protection, and you have a different CTs. So basically, with a normal differential protection, this is a problem. Like if suppose there is a fault on external, so what differential protection must obey is that for external protection it should not operate. But what happens if there is a heavy fault on the external to the zone, and if this city or this city gets saturated, then this act as a differential protection, because this city will read some let's say a 10 ampere, and this city will let's say read 8 ampere. So difference is 2 ampere, and this 2 ampere will be acted upon, and this differential relay will operate because this city is getting saturated. So this is a differential. Again, for a differential protection, we have uh, a logic. It is called percentage bias scheme, wherein we with the I differential we have I restrained current also. So that to some extent we can avoid the saturation problem by using this philosophy or this scheme. But again, if there is a very heavy saturation, this will also not work. Okay, and how that we are might be talking more detail when we are talking about, when we will be talking about the differential protection in detail in a upcoming webinars. At the present, you can understand if your differential is activating without for external fault, so you must look into your restraint settings or the slope settings. And at the same time, you must see your disturbance recorder for the city saturation on the both sides. Both sides means at one side, let's say this is your current, and if on the second side, if this is something else, so that city is saturating. So that we have to immediately replace. Okay, so mitigation, again, as you all know, you will say mitigation. The first mitigation is the use proper sizing, that is use knee point voltage high enough so that the saturation will not occur. But it is not always recommended, or it is not always practically possible, because if there is a heavy fault and you have to build a city without a saturation or a high voltage saturation point, then the city size becomes almost equal to your switchgear size. So to accommodate those kind of cities, indoor switchgears or outdoor switchgear is not always possible. So that point, till what extent you can size it properly, you have to size it. Second thing is that you should lower the burdens. So lower the burdens means you can use the low burden relays. That is where you can reduce some sort of saturation. Second one is that again is a part of a burden, a lesser cable lengths. So in one of the projects when I where I worked, on the same differential, everything was same, but the cable length of this differential relay was almost 3 times than this. So this is 1 time, so this is 3 times. So because of this, there was a mal operation. So because of this, there is a possibility that these small points can lead to the saturation and the mal operation of the relays. So lesser cable lengths or possibility to have equal characteristics of the CT to all the phases that you have to see. Then you have to demagnetize the CT after a heavy transient fault. So now if you know in your facility if there is a heavy fault, so you have to remove all the magnetism. So the remnants which is there in the core, that you have to remove. Otherwise, to the next operation, the CT will saturate it heavily because it is already magnetized. So that one thing you can do. So here remnants, I'm not actually the time we are running late actually. So remnants I will keep it for next time, because here I just wanted to explain more detail about the remnants. Okay, then fifth point is use of advanced numeric relays. So use of advanced numeric relays means uh, the second harmonic blocking features you have to activate. Then there are some relays which can analyze the waveform and change the signal filtering. So as I said, they can change from a cosine filtering to the peak filters. So that is also possible. So these are all the mitigations that is possible. Again, I could not think much at this moment, but as on when the case, if you are coming up with your particular cases, we can have a mitigation systems properly done for you. Okay. Then again, the saturation, how we should be selecting our relays, sorry, the CTs. For that, I'm just having one question here. Let's see how you are answering to this. So, which city class is best suited for a transformer differential protection? Whole. Yeah.
So mapping you out of your things, whatever you're doing, in case you're not present here, just to get an idea. So we have, okay, I guess we can, yeah, this is the result. Almost 53% have voted for the first one,
Okay.
which was more than which was kind of expected. The answer would not be what you would have expected.
Okay. Closing the ball.
Yeah.
So 5P10 you have answered for a differential protection, because just now what I explained, the differential protection is a very sensitive protection because it is a unit protection. It should not operate on any fault which is external to the zone of protection. So it has to see it has to be very sensitive for a lower faults. If you know the differential protection, how it works like this. So this is I differential, and there is a I restrain current is there. So here it should operate, and here it should restrain. So if you see at lower currents, that is for internal faults, the differential magnitude is very low. But as the fault goes higher, the differential becomes high. So it is expected that for external heavy fault it should not operate, but for internal small fault it should operate. So here the P10 means, as I told, 10 is 10 times of the primary, it will not saturate. So for this particular differential protection, these cities are not suitable. We have to go for a PX city. PX city, what is PX city? That I don't know if you must have heard it before, or for first time you are hearing this. I'll just run through the different classes which is available on the IC portal. So these are the IC protection city designations. So we know P is for protection, then there is a PR, then there's a PX, then there is a PXR. This is for a transient performance, transient short circuits. So these are very carefully we have to design these cities, because this works for a very high transient saturation. The PX and PR, I just have a short explanation on this. P means basically a protection city, wherein 5P or 10P, that the class that we normally see. Okay, and after that you have a 10, 20, even 30, even in some cases 40 also possible. So 40 means that is ALF, that is the accuracy limit factor. PR is somewhat same, but here R is for reminence. So reminence is taken care of. So PXCT is also for a protection, but basically this protection, this class of cities, everything is properly defined, and these cities are particularly for are to be designed based on the requirements of the protection. So if it is a transformer differential, then you must know what is the requirement of the here the reminence is not taken care of because R is not there. So this is R. So PXR, here the reminence also taken care of. So these two cities, two city class is basically used for unit protection, where the saturation is properly defined. Here, okay, we know the ALF and we can go ahead with this ALF. We know the reminence, we can go ahead with this PR cities. But normally you will see everywhere the P city. Again, this is for a transient performance cities. So this is the designation classes for IC protection. Okay, and we now will actually we have spent more than a 60% of our time onto this.
I think we're almost at the end. I was just wondering if you want to shift the relays to the next series. We don't have time for Q&A also. Are we at the end of our CT?
Yeah, CT is done. Now we are moving. It was almost, I think, we spent 60% of the time. So selection of the relays, we'll just run through. If maybe a 10 minutes time will allot for this, and in maybe next webinar we'll see. Yeah.
And anyone has any questions in the meanwhile, any cases, any issues, please feel free to drop in the Q&A. Yeah. You can go ahead.
Okay. Okay. The selection of relays. Again, there are a lot of big numbers the NC has given to each and every functions. So those are displayed and available everywhere, and you must be aware of many of them. So these are numbers. So normally what we see is 50, 51. So 50, you can see here, 50 is instantaneous current relays, and 51 is time over current relays. So mostly we are working upon a 50, 51. So other is basically for a very typical requirement of the protections. Let's say here you can see 49 49 we basically use in induction motors, high voltage motors, but I have not seen here 49 is getting used at the transformer levels. In particularly, I'm talking about the data center, but we normally do other industries also, where mostly we use many of these numbers or many of these functions. So data centers, I think 49, very few people must be using. Then I think um, 87 everybody must be using. REF everybody must be using. 51V, this is one thing which I was interested to talk about more, but we will be covering in the next two sessions. So 51V is for a protection at generator terminals. Then 51LR, this is R. Okay, 51LR is for stalled rotor. Recently, I've done one data center wherein the chilled water pump is of 11 kV motors. So there, I have tried to give this 51LR, but again, not implemented yet. But other industries everywhere where the 11 kV motors are there, we are using this 51LR for this. Then for a negative sequence relay, basically should be used for generator protection. Okay, so these are the typical regular differential. You can see 87 here. Oh, my mouse is visible. Right? So 87, 87B is for bus bar differential. That is there. So we are. Let's see how many of you knows what kind of protection is preferred for unbalanced loading in a generator. So poles. Yeah. Okay.
Yeah.
Okay, got it. Okay, what is the answer for this as per poll?
All A and B are the most voted.
Okay, so basically 51 is earth fault, right? So
Yes.
I was thinking the unbalanced loading means you may feel there is a kind of earth fault. Okay, but okay. So the answer is basically it's a B. It's a negative sequence relay that we are using for unbalanced loading. Because if you see the unbalanced loading, uh, uh, this is everything is going perfect in the balanced conditions. Okay, but in unbalanced condition, it's not at all perfect, right? So if you resolve these components, you will see negative sequence current is more. So I2 you will find more, and it's very easy to have a 46 installed, and it will measure the negative sequence current. Maybe you can set it to 10 to 20%, and time delayed as well. Okay, now the selection of the relays. How much time we have?
I think they're already over time. So
5 minutes.
5 minutes, okay. So we all know that high voltage networks, the main requirement is the relay has to be sensitive, rapid, minimize the electrodynamic and thermal stresses on the equipment. So for that, the protection against phase fault, we are using 50, that is instantaneous overcurrent, 51, that is time overcurrent, IDMT. So 50, 51, I have already explained how the characteristics of these relays are in the previous webinars. Application for 51, we basically have to go for a 51 where we are expecting a short time overloads. So overloads more than a pickup value, but for a very short duration. then you have to go for a 51. The inrush current exists for several seconds. Though we have a second harmonics blocking, but we can have the 51 install, maybe extremely inverse or very inverse nature, which can take care of the inrush currents. Then we have a definite time, that is 50. Where there is a wide range of a short circuit currents, we are normally using 50. And second one is when there is no current grading possible, only time grading is possible. There we use definite time, that is 50. Okay. Then we have accelerated selectivity logics, which is reverse blocking. We will be talking about more on this reverse blocking in the next webinar. Then we have a directional overcurrent relays. So in a network, when there is the bus is fed from two sources, right? So there you must have a differential protection given to this, because any fault, suppose there is a fault on this side, this generator is also feeding the fault and this also feeding the fault. Ideally speaking, this relay should trip, not this, because the fault is not on this section. So for this, you must be using directional overcurrent. How to use, where to use in detail, we will be going into the next webinars. So where there are parallel feeders, parallel sources, you must be going for a 67. When the network is ring, not radial, you have to go for a directional overcurrent. Then, sorry, protection against earth fault. Here again 50N, 51N, 67N. With respect to earth fault protection and earth fault requirements, that power transformers, the requirement is minimize electrodynamic thermal stresses on the transformer, protection against phase fault. So for a transformer, we are looking for a 49 thermal overload relay. In a power transformer, we can have this thermal overload. Basically, in transformer, we also have a mechanical relays. So mechanical relays means Buchholz relay, pressure sensitive relays. So those relays are mechanical relays. That is for the internal fault that we are using. We're also using a temperature sensor here. So the temperature sensor and thermal overload should have a almost similar characteristics. Okay, so 49 has a direct temperature sensing or a inbuilt relay algorithm. So the direct temperature sensors are there, then we can give the input to the 49 relay, or we can use the relay algorithm for a thermal overload.
So while we are on 41, there's a question whether we can use it for HP motors also. 49 can be used in HP motors also.
49, right? 49, yeah, definitely. 49 you have to use everywhere. On HV side, we normally go with this relay. 49 thermal is all required, because insulation damage should be protected, and not for the short circuit only, but should be for the overload also. So it is a replica of the temperature sensor. So and the thermal overload relay, you can have the below your stator damage curve. You can set it to the for a thermal overload. Then again, a regular 50-51 you are using for transformers. Use of IDMT for longer duration of overload, sympathetic inrush, reacceleration, and selectivity. We are using IDMT zone. And for a DT, we are keeping it for a fault which is above through fault level, that is secondary fault. Protection against earth fault for a transformer, again it is the same. So 51N is slightly time delayed and pick up more than 6 to 10%. On the primary side, we are keeping. Our instantaneous pickup shall not be less than 15 to 20%. This we will be covering in our next webinar, wherein we will be talking much more detail about the protections. On secondary side, overcurrent relay on a neutral earth connections, that we can directly give, which is commonly known as a standby earth fault protection. Then we also can give on the secondary side a differential protection, that is restricted earth fault protection, that we can use on the secondary side. Then there is a tank protection. So basically, the earth connection between tank and earth. So in that bus bar, we put the CT and we take this to 51N relay. Again, the differential protection 8070 you all must be knowing. Okay, again directional, where the transformer is in parallel with the another source. So if the two transformers are running in the parallel, you have to consider directional 67. There is a overfluxing protection. Now you must be knowing what is overfluxing and how overfluxing can be damaging. Overfluxing means saturation. So saturation means on the primary side, and this is your transformer, right? This is your secondary, this is your primary. Now what happens in reality? This is your voltage. You apply the voltage, then there is a magnetizing current that flows. The magnetizing current is very low because there is a generation of a back EMF. Back EMF, right? So that EMF is generated. That EMF is induced because there is a d phi by dt. Now, because of the overfluxing, this d phi dt becomes zero, almost zero, not zero, but close to zero. So there is no back EMF. Now it is voltage directly going across the resistance of the winding, because there is no back EMF to restrict the current. So heavy inrush current or heavy current will go and the winding will get damaged. So to avoid this, 24 is installed. For a bigger transformer, we are doing this. For a smaller transformer, overfluxing we are not using. So for generators, generators are a long list, because generators, the relay function is based on power rating, prime mover, steady state short circuit current. Steady state short circuit current, if you know the decrement curve or the reactance that comes across at different times. So these three reactances come across different times when there is a fault. Initially, it is a subtransient, then there is a transient reactance, and then there is a steady state reactance. This is very high, maybe 25% to 30%. Okay, this is at a lower level of a 10%. So when the fault, this two diminishes in maybe 5 cycle or 10 cycles, and after that this comes into the picture, which is very high. Sometimes the steady state current can be less than the rated current of the generator. So it is very difficult to analyze or to trip the generators in a steady state zone. So main two cases we have to consider. One is diesel generator, which is of very hundreds of kVA, 3 kVA, 3 MVA maximum I have seen. Then turbo generators, we have tens of MVA. So there the protections will be very stringent. In the protection against external fault, we are using 51 voltage restrained overcurrent relay. How this works, we will try to get the details of this into the next webinars. 49, as I told you, this is for thermal overloads. 46 for unbalanced. 46 for unbalanced means this is negative phase sequence relay, wherein I square T constant, if you have seen, that is taken care of. So the characteristics is approximating this particular curve. So this curve is like this. So this is your TCC, and this should be following this. So this should be protecting this I2 square T curve. Okay. Then we have a reverse power protection. Then we have a frequency variation protection. Then we have 2759. You must be aware of this under voltage and over voltages, because on the generators, mainly if there is a load shedding on a severe magnitude, the voltage on this bus may rise very heavily before your AVR comes in the picture. So for that, over voltage and under voltage protections are required. The stator or fault protections, I think this I need some extra time to explain how this works. We have a stator or fault damage curves also that we'll be explaining in the next session. So these are basically NC codes function that we are using. Overfluxing, if we are using here, you can see neutral displacement 59G also we are using in bigger turbo TG turbine generators. Field failure also we have to go for. Motors we have the same requirements. Thermal overload protections as you asked for. Motors we are considering 59. Then we are considering 51 LR, that is for lock and startup. So startup, you know that there is acceleration time required for the motor to accelerate, and then at the same time there is a lock rotor withstand protection. In some cases, now you will find in big motors, this startup time is actually greater than your lock rotors. So lock rotor, now you cannot protect this lock rotor, and at the same time you cannot have the starting curve protected. So here, if I go for this kind of a relay protection to avoid the starting tripping, but my lock rotor withstand is below this to the left. So I'm not protecting my motor from the for the lock rotor. So here we have a different schemes that is to be worked on, that is long LPS that we will be talking later. And then busbar protection is again same. Main busbar protection that I just wanted to talk more about is arc fault detection sensors. So now we have every nowadays we are installing arc detection sensors at HV MV buses. Okay, so I think we can move
Yeah,
ahead.
we've largely covered, I think. Yeah, sorry, it was a little over time that we ran. But yeah, the topics, as you can see, they do demand a lot of deep dives. And although we try not to make it too boring and theoretical, but inevitably it becomes too theoretical because that's the nature of the game. Um, I think in the next couple of webinars, we are going to be more and more diving into more real life case studies. Once the base foundation of this vast topic has been set. So please stay tuned, and we'll request to please pass on the YouTube links, which my team will share on the I've already shared in the chat for you to subscribe as well as watch the previous recordings, and you can definitely share it to your colleagues. The more it gets shared, the more motivation it gives us to continue the series. And once again, thank you so much. And sorry, if anyone has any questions still further, please feel free to raise your hand. You can even speak, or you can even type in the Q&A. We'll wait for a couple of minutes in case there is some question that anybody wants to ask.
Can you also use 49 in HV motors in DC?
Yes, that we already answered. That in fact, 49 was already covered in motors. It's one of the thermal overload protections that is definitely. Please do also provide your valuable feedback as always to give us any areas of improvement, any topics that you would want us to cover. It will help us to keep the series more alive and interactive. So with this, we will, I think, end the webinar. And thank you once again for attending.